One of the great controversies that we are living through right now is the Hubble tension, or trying to measure the Hubble constant. This is the rate that the universe is expanding, and the evidence seems to be growing that there is a problem with the underlying models, the lambda CDM model that astronomers have relied on for decades. And whenever you have situations like this, the hunt is on for better measurements, better data. Really, a lot of this depends on the distance ladder, this tried and true method of measuring the distance to objects in the universe where they rely on each other step by step by step. But astronomers are always on the hunt for new methods of measuring, ideally ones that are independent, that don't require that distance measurement. And we've got a new phenomena that we can use to measure distance in the universe, the fast radio burst. We actually don't entirely know what fast radio bursts are, what's causing them. They're probably coming from neutron stars, probably coming from magnetars, but this is still an unfolding mystery. And yet we can use fast radio bursts to measure distance in the universe. My guest today is Dr. Matt McQuinn. He's a professor at the University of Washington, and he was awarded a NIAC grant 2 years ago to build the cosmic positioning system, which would be like a GPS, helps you figure out your location on Earth, but would be tracking fast radio bursts out to 500 million light years away with a level of accuracy that you could directly measure the expansion rate of the universe. Imagine Gaia all the way out to 500 million light years away. But it would require a constellation of satellites that are 50 astronomical units apart. So this would be quite an undertaking, and yet it would give us the best answer we could hope to have for the expansion rate of the universe in our vicinity, which is one of the trickiest ones to measure. So we're going to talk about all about fast radio bursts. We're going to talk about this idea of building this cosmic positioning system. I think you're going to love this interview with Dr. Matt McQuinn. Matt, we're going to spend a long time talking about fast radio bursts in this interview. And, you know, my audience is very familiar with this phenomenon, but let's give people who maybe aren't familiar an explanation of what a fast radio burst is.
Yeah, there are these millisecond radio transients that we discovered, I guess. The first discovery paper was in 2007. So there was this burst that was called the Lorimer burst that was discovered on the Parkes telescope. It was this millisecond 1.4 gigahertz, which is like one of our favorite radio frequencies, transient that was discovered out of the plane of the galaxy. And for radio waves, you can tell how many electrons they've gone through. And 99% of the atoms are ionized in the universe. So most electrons are not bound to nuclei. And so the column of electrons out of the galaxy was so high that they inferred that this must be something that's extragalactic. Of course, this was controversial, so people didn't know what to make of this one burst. And then in 2013, 4 more were discovered, and they also had these same properties, lots of electrons out of the plane of the galaxy.
I remember at that time, there was a paper coming out where they had used a telescope that allowed them to figure out how far these things were, or at least that it's not within the solar system. Like it would have been out of focus if it was inside the solar system. And so we don't know what these are, but they're definitely not bouncing off satellites, things like that.
Yeah. And actually, this is kind of when I got into the field, when these 4 extra were discovered. And they all had been discovered at the same Parkes telescope in Australia. And there was actually this other millisecond transient that also had a similar sweep in frequency to like that looked like it was going through a lot of electrons, but it clustered around lunchtime.
And right. So it's like microwaves at the
So
telescope.
they, like with some sleuthing, like they eventually figured out that it was microwaves that were being opened while they were running, like at the end, like if you were impatient, and it had like the same properties as these bursts. Although you can kind of tell how far away things are. So they knew that before they knew they were microwaves, they knew there were some hints that they were nearby. But then people had theories about maybe some are further away and some are nearer, but they're the same thing. But then they discovered that microwaves was some of these, and the rest were actually real. And then eventually we were able to figure out. It took a few more years, like that it's in that galaxy. Then you really know. There were even theories that maybe it's like flaring stars, and I was worried because I wrote a paper on what you could do with these early, for kind of the first theoretical paper, one of the first theoretical papers, and but I didn't, I, I, yeah, I didn't totally believe that they were real. But then eventually, at 2016 ish, they figured out, oh, it's in that, this one's in that galaxy, and then they started rattling off more, and now we've figured out, we've done this hundreds of times, so we know, sometimes we don't even know, not only know what galaxy it's in, but like what not in the galaxy it's in.
Right. Okay. And then give us a sense of like the distances. How far away are we finding these things now?
Yeah, the record holder is redshift 2.5 ish. So
Oh, wow.
they're coming from almost certainly neutron stars, or at least some of them. Probably highly magnetized neutron stars, which are called magnetars. There was one in our galaxy that was like a really wimpy FRB, but looked like an FRB that was from a magnetar. So that's our leading theory. Although there's some like properties of the population that are weird. So people will tell you that a lot of people think that there are multiple sources. But there are 10,000 on the sky a day at the sensitivity limits of our radio telescopes. So there are a lot of these. Some of them are like pretty close actually. So we found I think we found some that are just a few million light years away, which is close by for a cosmologist.
Like in Andromeda or something, like
Yeah, further
relatively
than
close.
Andromeda, but like in like a relatively local galaxy. Yeah,
Yeah.
the redshift 2.5, you should think a few tens of thousands of millions of light years.
Yeah. Redshift 2.5 works out to 2.6 billion years after the Big Bang.
Yeah.
Yeah. Yeah. So that's kind of exciting because you've got this single source that we have them relatively close by within just a few million light years, and then ones that are closing in on the Big Bang itself, and they share all of these common features. And so, I'm sure as an astronomer, you look at that and go, well, that's a Swiss Army knife if I've ever seen one.
Yeah, and actually, it's been like a super dynamic like field in the last, because it's only been a decade where we really knew that these were extragalactic, and so now hundreds of people are working on them because they're just so exciting. Like a large fraction of the radio telescopes on Earth, like this has become one of their primary sciences. Is a very exciting development.
Obviously I live in British Columbia, and we have one of the coolest telescopes in British Columbia, which is the Cain instrument. And this has done some of the heavy lifting on this work so far, but kind of accidentally. Like, it wasn't originally the plan for that telescope. But now you've got things like, say, the Square Kilometre Array being built in South Africa and in Australia, and that is, intentionally going to be looking for these things, right?
Yeah, that's right. And yeah, Time has discovered by far the most of these. They don't have great localization, so they can't say it's like in that galaxy usually. But yeah. I'm actually not that far from you. I'm in Seattle, but that SKA will be really good for this. They're building the next generation of Chime, which is called Cord, which is going to discover tens of thousands of these. There's a funded array that's called DSA 2000 that is led by Caltech that is also going to discover tens of thousands of these. We're going to have many FRBs in the coming decade.
So whenever you have this signal that's coming from really far away, as I mentioned, this idea of astronomers see this as a Swiss Army knife. Hopefully you're looking for some kind of attributes that make something a standard candle, something that you can measure distance in the universe in an independent way. How do these sort of shake out as a potential standard candle?
Yeah. Okay. So there are two ways of getting distance. The standards for cosmology are high because we're measuring everything at the percent level. The way that we're measuring distance currently, that we're not really using for cosmology, but it has other interesting science, is that I mentioned that we can measure the total number of electrons, called the column of electrons. So the density integrated along the sight line of electrons.
So sorry, let me understand this. So this is like the number of electrons that are in the way of the burst as it's making its way to us.
Yeah, exactly. And so
Okay.
so what happens is that the light is electromagnetic waves, and so it's traveling and it shakes the electrons along the way. And if you shake an electron, it radiates. And so but it'll radiate at a slightly different phase than the light that was emitted by the burst. And so this causes the wave to travel at a different speed than it would otherwise. We're very familiar with this. This is why light bends in water. The light is shaking the charges in the water, and this causes it to travel at a different speed.
I think that's possibly one of the most dangerous questions that anyone can attempt to try and answer. Was like, why does light move at a different speed in a medium? That's a very scary place to try and explain that, because then the physicists will pop up and go, well, actually, that the way you've described that is incorrect. So I'm not going to touch it with a 10-foot pole. But you, as a cosmologist who studies this kind of thing, I look forward to the debates in the comments down below.
But the net effect is that for these FRBs is that so different wavelengths travel at different speeds. The same light and water. And so we can watch. So when we detect an FRB, the shorter wavelengths arrive earlier than the longer wavelengths at our telescope. And because we see this, we measure the total number of electrons they traveled. So this is a beautiful thing about FRBs. And so if you know the density of the universe, which we know how many atoms there are in the universe. Actually, the cosmic microwave background constrains this very well. Then you can give you a distance with some caveats.
Wow. Okay, so that's really interesting. So the light, depending on how many electrons they've gone through, the light arrives at a slightly different time, kind of like the difference between, say, light and the neutrinos associated with a supernova or something like that, right? They're not going exactly C because they've gone through intervening material. And you know that there's whatever it is, like 10 atoms per cubic meter or something like that in the universe. And so you calculate that delay, and that tells you how much intervening material it had to pass through. So that gives you distance, right? Because you're essentially measuring the volume of the cylinder that the light has gone through.
Yes. But it's not a very good distance in that.
Okay.
And this is actually the first thing I wrote about. It's not a good distance because the universe isn't homogeneous. Like, it's not like the same density everywhere. Sometimes you'll go near a galaxy and the density of electrons will be higher and sometimes lower. So there's a lot of fluctuations. Like one sight line through the universe, there'll just be more electrons and some less, and so the scatter is large.
But isn't it the largest scales, the universe kind of like the same to like 1 part in 10,000? Like, isn't the universe mostly just normal?
That's right. That's right. On the largest scales, on the scale of our horizon, the fluctuations are part in 100,000.
100,000. Okay. Yeah.
Yeah. It actually turns out that if you send a line through the universe, the fluctuations are much larger than if I drew like a big sphere.
I see. Okay. And especially if it's leaving a galaxy in the beginning, which is already going to be kind of a messy place.
Yeah. Okay, that's good. That's even.
Or coming into our galaxy, right? You have two galaxies definitely in the way.
We know how many electrons kind of are in our galaxy. So we were talking about a lot of electrons from in between galaxies. So you might think maybe this is okay, but yeah, it's coming from like some special spot in some galaxy. And so like, how can I use this in a way? Like, if I really wanted to use this to measure distance, I have to do this at the few percent level for it to be interesting, because we have other ways of measuring distance. So what I wrote about was not measuring distance. I wrote about how, actually, one thing we don't know, and this is the first paper is on FRBs. The one thing we don't know is how clumpy the gas is in the universe. Actually, most atoms in the universe are not in galaxies. They're they're outside of galaxies. Only 4% of the atoms are in galaxies. If there weren't supernova and black holes, we would expect that it would be more like 40 or 50% of the atoms would be in galaxies. And so the galaxies have actually been really efficient at pushing back on the atoms. And how much they have done this, we don't have a great understanding of. And so it turns out that this probe, like these fluctuations, like some sightlines much higher a number of electrons and some much lower, you can use to probe the distribution of atoms in the universe. And when I say atoms, really it's electrons. And they're not bound to atoms, but there's a nucleus around. And so why would you want to measure the distribution of atoms? It's actually something we don't understand at at like a really qualitative level. Like, it's a big uncertainty in our universe. Sometimes this is called the missing baryon problem.
And not even just like dark matter, but like regular matter seems to be missing.
Actually, at some level, we think we understand where the dark matter is better than we understand where the atoms is, because the atoms are so complicated because of all this physics. We don't think that dark matter has as much physics associated with it. And actually, we can even, that I say think, but we can actually measure where the dark matter is. We're really good at mapping, like gravitational lensing. And so we know where the dark matter is much better than we know where the atoms are. And so it turns out that this is actually a huge uncertainty in cosmology with like Rubin, like where the atoms are, because they want to map where the mass is with weak lensing. But 20% of the mass in the universe is not dark matter; it's atomic matter, and we don't know where 20% of it is very well. And so like this is actually a huge limitation for our weak lensing surveys. And cosmology has invested substantially in weak lensing, like Rubin, Roman, the Euclid, like all of these like current and future telescopes, the like big investments are they're one of their primary sciences. The primary cosmology is weak lensing.
So if you're then discovering these tens of thousands of fast radio bursts, and then you're putting these as a map, an overlay on top of your weak gravitational lensing measurements, you're then able to double check, right? And that is the dream.
Yeah, exactly. You're able to correct, even like you're able to take out this uncertainty. You're able to make these surveys more powerful. And so that's actually a lot of the fast radio burst community that's what they're aimed at doing. And that was my initial point when I started in this field.
It's amazing that, because normally when we talk about the standard candles, we talk about the Cepheid variables, we talk about type 1a supernovae, and then other less accurate ones, that you're looking to know the intrinsic brightness of this object. But what you're describing, you don't need to know the intrinsic brightness. You just need to be able to measure the light with enough accuracy that you now have an independent method that works at all scales in the universe. And this must be incredibly exciting to astronomers. So what's it going to take to bring that accuracy down? And maybe this is how we sort of segue into your NIAC grant.
Yeah. Okay. I think this coming generation of fast radio burst surveys are going to get rid of a lot of this uncertainty in where the atoms are, and it's going to make these surveys with Rubin much more powerful. And so the NIAC is going in a different direction, which is that. So we want to make these surveys much more powerful. But at the same time, there's like something very interesting happening in cosmology, where you mentioned supernova. So we have a variety of methods for constraining the parameters of our cosmology, like dark energy, the amount of dark matter. Supernova is one. The cosmic microwave background is another. Weak lensing is another. Baryonic acoustic oscillation surveys. So what is currently happening is that they're all kind of disagreeing with each other, or suggesting really weird evolution for the dark energy. Or there's this Hubble tension, where maybe our best explanation, if it's real, is that there's some phase where there's early dark energy, like in the near recombination. And so there's these tensions between all these data sets.
Yeah. We actually reported on this a couple of months ago, that there was the sort of final, and I always mix it up, was the Dark Energy Survey or the DESI. I think it was DESI. They had finished up their 8-year observing run. And as you mentioned, those 4 methods of measuring dark energy two of them sort of more continued moving in that direction, and then two of the other methods went in the opposite direction. And so you got kind of conflicting results from what are thought to be these four independent ways of measuring dark energy. So that didn't help, right? So it's still confused. Like maybe it's evolving. Like there's more evidence that dark energy is evolving over time, and there's also more evidence that it's not evolving over time.
Yeah, it's been a long time that our cosmological model, which we call the lambda, which lambda is the cosmological constant, cold dark matter. So lambda is CDM cosmology that has worked so well for decades. And like maybe it's breaking. Like maybe dark energy is evolving, and so maybe we want like an even more robust way of measuring distance. And the most robust way of measuring distance is to use geometric methods. You're not calibrating the luminosity of supernova with the distance ladder, or a lot of these other methods actually have to assume the model in order to measure distance, because it relies on sound waves in the early universe and how far they propagate. Also, a motivation is we've surveyed a lot of the cosmic volume now. Our current methods, we're actually pushing up against we just aren't going to be able to do much better potentially.
And so when you're saying geometry, you're talking about like astrometry. You're talking about parallax, like a better Gaia. But now you're measuring the distance to fast radio bursts.
Yeah,
measuring parallax as opposed to the method that you were describing earlier.
Yeah, exactly. And you can phrase it I might not phrase it initially in terms of parallax, but like you can phrase it in terms of parallax. And so parallax is wonderful, right? I look from different directions and it gives me the distance, and that's pretty robust.
Yeah, that's the gold standard.
Yeah, but Gaia is amazing, but you're not able to measure parallax angle for distances that are cosmologically interesting.
Right. So you can't measure anything outside of, like, say, the Large Magellanic Cloud.
Yeah, that's right. And really you want to go much further. You want to go to more like 500 million light years away. Because then what we say is those distances, those galaxies at 500 million light years are in the Hubble flow. And you want to do this at a percent. And so if you can measure distances out at 500 million light years, then it sounds really bad. So yeah,
no, I love it. Man, I eat this kind of thing up. This is great.
Yeah. And we're going to tell you what it takes. It's going to take a lot. We're talking about parallax angles that are 100,000 times smaller than Gaia. And Gaia is amazing. So how the heck would I do that? But maybe let me just digress and say, like, what exactly are we doing? So you measure distances. When you say they're in the Hubble flow, it means that the velocities of the galaxies are all moving kind of relative to each other because they're pulling on each other. But there's also the expansion of the universe. And when things are in the Hubble flow, the expansion is dominating the recessional velocity rather than the local motions. And so at this 500 million light years, the local motions are at the percent level. If I measure the distance, I know it's in the Hubble flow. And so then if I measure distance and velocity, if I know what galaxy it is and I can measure its velocity away from us very well, then I can make a Hubble diagram, a distance velocity plot, doing the same thing that Edwin Hubble did in 1929. And actually how that evolved, the slope of that is the Hubble constant, which different measurements are disagreeing at the 10% level. And how it evolves depends on how much matter there is in the universe, how it evolves with distance, or how much dark energy there is, the evolution of dark energy, potentially the curvature of space-time. And so that's a curve that we really like to measure if you're in cosmology, because it's giving you these things. And this is because
And like up to this point, all of your measurements of the the Hubble constant are this sort of second order, that you know the intrinsic brightness of a Cepheid variable, you identify Cepheid variables in this other galaxy, you then measure the brightness of the Cepheid variable that tells you the speed that the galaxy is moving away from you. You know the intrinsic brightness of a Type 1a supernova. But if there's any measurement error, any of those, and Adam Rees guarantees that he has made no mistakes, but still, if there is any new science that is discovered about how Type 1a supernovae work, then maybe you can then come back and refactor. But if you're just doing astrometry with geometry, you're getting the exact distance to that thing.
Yeah, you're circumventing the distance ladder, which to me is a little bit of a messy set of rungs. To Adam Rees, he will argue with me, but
I'm sure.
So what would it take to get rid of this completely?
So I'm sure he would be perfectly on board with you offering up a geometric way to measure distance to these things. He'd be all right with that, I think.
Good.
Yeah.
Or confirm, maybe it confirms his
totally
his Hubble constant, and then if it's confirmed, that is crazy interesting because it's implying something hugely wrong with our model.
Yeah, which again, I think you need to go on the record. Wouldn't it be great if your models were wrong? All of the always having these arguments with the science deniers, and they're like, astronomers are just too religious in their beliefs. They just want things to, they assume the outcome. And no. You would be giddy if
we want it to be wrong. It's been, this model has been around a long time. We want to find something new, that adds to the to the record. So we would be so excited.
What do they say? Not all models are right, but some are useful, right? And that's the thing with Lambda CDM. It's the best one. It's stood the test of time so far.
Yeah,
there must be cracks in it, but how to tease them out. So let's talk about this. How do you get a geometry measurement of a galaxy that is 500 million light years away?
Yeah, good question. And maybe I'm going to start with an analogy to the global positioning system, GPS, which is, you have your phone and it tells you to a meter where on Earth you are, receiving a signal from at least 4 of the GPS satellites. And so each of these satellites has some radio waves that are coming out, and there's on top of this sine wave, there's some code that modulates it, -1 1 -1 1, and each of the satellites has a different code, and your phone knows the code for each of the satellites, so it's searching for them because it knows when the code was sent. It knows exactly how far it is away from that satellite, because we know the positions of the satellites very well. There are 4 space-time positions for your phone, and so you need 4 satellites. If your phone had an atomic clock on it, then maybe you would only need 3 satellites, but it doesn't. It doesn't have a great clock, so you need 4. This would work if my phone sent out a signal to the satellites, and then they timed when it arrived. They'd be able to, from some math, figure out where my phone is.
Right, and then just reply back to you, here's your position.
Yeah, exactly. Yeah. Exactly. Now, if I'm in a city with a lot of buildings, then I can only see the satellites directly above me. And even if there are 4 satellites, I'm not going to have as good of a position. That's kind of the preface. And so then we're going to do the same thing for fast radio bursts. Rather than my phone broadcasting a signal to the satellites, the fast radio burst is giving us the signal. And it really, when the radio light from a radio source is some unique, random waveform. So here we're talking about, we're going to send satellites out, and we're going to ask how far apart do they need to be in order for this to be interesting, because we don't want to be in the limit where they're all just directly above us. And so that we need to be in a limit where we can measure at 1% the distance, the location of the FRB, from the positions of my satellites. So we're gonna have to have a satellite network, and when I say satellite, it's really spacecraft. We're gonna want to launch them far. We're gonna launch spacecraft, and we're first gonna ask how far do they need to be apart, in order for them to be able to receive the FRB light, and then by comparing when it arrives at the different spacecraft, measure the distance to a fast radio burst at 500 million light years.
Mm-hmm. How big? How big a triangle do we need?
Yeah, that's right. And so let me, like, one other piece of information that you need is that how well can I, like, if I have the light and it arrives on one of my spacecraft, how well can I time the different, the time difference between when it arrives at different spacecraft? We're talking about gigahertz, or actually it turns out that this is best at a few gigahertz radio waves. And so it turns out that you can roughly time the light to roughly to 1 over the frequency of the radio wave, also divided by the signal noise that you detect things. So if we're gigahertz, 1 over the frequency is a nanosecond. So you can really time to fraction of a nanosecond when the light arrives at your different spacecraft. This is what we do all the time for interferometry.
Right. I mean, this sounds like very sort of neighbor to interferometry.
Exactly. And actually, maybe even the motion of continents, we've been from looking at quasars on the sky, and with radio dishes on Earth, we can see them drifting relative to each other when we take the light from the quasar and we match it between the two, because we're able to match so well that we can see like millimeter per year type of drift. And so that's doing the same thing. It's timing the light arrival from the quasar. Here we're doing the fast radio burst.
That's crazy. 2 telescopes looking at the same quasar, you can measure continental drift by how the light is changing.
In practice, you use more than one quasar, but yeah, that's right. So with radio waves, we're timing light really well. Actually, for Event Horizon Telescope, where we're using hundreds of gigahertz radio waves, you're doing even way better than nanosecond.
Right. And, if thinking about, say, the Event Horizon Telescope, they had all these telescopes. They all were equipped with best atomic clocks on Earth. They all, at precisely the same time, started to record the wavefronts coming from the shadow of the event horizon. And then they took all these hard drives, gathered them together, lined up the wavefronts to the point that they were then turning this into an interferometer after the fact. And that allowed them to get this insane resolution. So you kind of, it's like this is the part that I just want to make sure I totally understand. So you have atomic clocks on your spacecraft. They're recording a fast radio burst together, and then they're transmitting their data home, and then someone is crunching those numbers to line up the wavefronts coming from those fast radio bursts. Like, it is an interferometer, right?
Yeah, you're exactly doing that. Yeah, and exactly. So these global positioning satellites also have an atomic clock, and you need about that quality of atomic clock on these spacecraft. So they need an atomic clock. They need to send the data back. And we haven't gotten to where the spacecraft are. I don't
know why you're making us wait on this.
And that's what this NIAC document is. And we're going to get into it. But let me say one other thing is which is, you lined up the electromagnetic waveform. We need 4 of these spacecraft, just like global positioning system. Need four satellites. Maybe another way of thinking about it is I need to constrain 2 angles, and I need to also constrain the distance, which is the curvature of the wavefront. And so then I have, with 4 spacecraft, I have 3 differences in time that are independent. And so I can solve for all 3. So we need 4 spacecraft. How far separated do they need to be? Well, I'll give you one other number, which is that, and this is going to sound large. It's a large number just because it's round. But if you put spacecraft at 50 astronomical units apart, then the fact that the wavefront is curved, like it's spreading out as a sphere, around our FRB. So like your FRB goes off and then it propagates out. The fact that it's curved results in a 10-meter difference in how long the light takes to arrive once it arrives on one of the spacecraft. The second spacecraft, if they're of order 50 astronomical units apart. 10 meters is a humongous effect because we can really, I was saying 10th of nanosecond, if I translate that using speed of light to kind of the how well in position you're able to say where the light is, that we're talking about couple centimeter. So like if I can measure a couple centimeter positions, so I time things to a couple centimeters, 10 meters, I'm almost like part in 1,000 measurement. So 50 astronomical unit, I'm almost doing a part in 1,000, and I sorry, and I've assumed something. I've assumed a distance for the source, which I'm doing this 500 million light years.
Yeah.
So
yeah. The worst case scenario.
So 500 million light years. This is a 10-meter effect. So if I get things at 50 AU, I'm doing amazing, way better than any cosmology has done. Again, there are like 10% discrepancies. And so, okay, so that's the idea. Like, we want to get the spacecraft as far apart as possible. They need an atomic clock. And so the idea that for this NIAC proposal is like, or what this NIAC proposal is about, is just what would it take? And basically, you don't want to stop them because that takes a lot of energy. So you just want to send them out, have an atomic clock. They need to detect FRBs. They need approximately an 8-meter dish, and we're really experienced at putting radio dishes in space for telecommunications. And actually, NASA's developed very lightweight dishes.
Yeah, that's not much bigger than the Voyager dish. Like, what, 3 meters?
Voyager was 4 meters, yeah.
Yeah.
Or maybe a little larger. Yeah, something like that. But so this is bigger. It would be light. So it needs an atomic clock and a big dish. And a really nice thing about these FRBs, so usually with a radio source, like, you just would never be able to get, you were talking about these hard drives. There's a lot of data on those hard drives. The data rates from the outer solar system are like very unwonderful. Like, we're talking about kilobit per second for New Horizons, or 10 kilobit per second. So a nice thing is these FRVs are like millisecond. It turns out that for each FRB, you only need to send, order 1 million bits back. And so if you do that over an hour, you're actually at kilobit per second. The FRBs are really nice because they're like very bright, and they're milliseconds. Some of them are even shorter than a millisecond. You can actually, you take your dish and you return and you'd send it back. And so the data rates work. The atomic clocks of course, I think we can get into limitations of this, but like the technology seems like something that humans can do. Like, it's not like we're talking about super futuristic things.
Yeah. Well, and it almost sounds like, I mean, you probably would want a dedicated spacecraft, but if we are going to go to the outer reaches of the solar system, if there's plans to go out into interstellar space, go to the solar gravitational lens, like there are this kind of, let's send a spacecraft, a lightweight spacecraft that does one job really far out into the solar system. There's a lot of people who would love to see this happen for a bunch of different reasons. So let me make sure I understand this correctly. So you're taking a spacecraft. It kind of looks like a Voyager in that it's got an 8-meter dish. It's got an atomic clock on board. You're sending them in 4 different directions. And once they get about 50 AU apart, which is like the distance from, say, the sun to Pluto.
And the 50 AU was for almost part in 1,000. It goes quadratically in distance, this effect, the curvature of the wavefront. So like, once they're tens of AU apart, like, this is starting to get interesting.
Yeah, okay. But there is no limit. I mean, say it took 10 years for New Horizons to get from Earth to Pluto.
Yeah.
In theory, that's when these things, or I guess half the distance, right? So 5 years, these things start to come online and make this 4-dimensional shape that is giving you this baseline. But then they just keep going. 5 years later, now you've got a 100 AU baseline. 10 years after that, you've got a 200 AU baseline, right? Like, it just keeps getting better and better, right?
Yeah, and because the effect goes quadratically in distance, if you were able to do this at 200 AU, like in our original paper on this idea, like you actually getting like interesting measurements for if there were FRBs on the other side of the universe, like basically very high redshifts of many. You'd actually be able to measure their distance. So like the effect just gets larger and larger. There are some complications that but I actually think maybe not so much at a couple hundred AU. But so one thing that you do need here is, so you also need to know the positions of your spacecraft really well, just like we needed to know the positions of the GPS satellites very well. And so what happens here is that the spacecraft then have to turn towards each other and communicate so they have to send the signal. Now it's really nice that this is ranging. They really wouldn't be able to send information to each other. Like information goes as 1/r². But ranging, where I send some code, and I know the code over here, it only goes as 1/r, where r is the distance.
Can't use pulsars to navigate and know their distance?
That's a really good question. It turns out that pulsars are pretty faint, but I think that would be like pulsar science is interesting for this. The angular resolution is so good that this mission could also kind of resolve the 10-kilometer scale of some pulsars. But yeah, it's true that if you have other sources, those also can help you calibrate the positions. So it doesn't have to be pointing to each other. But it turns out that if you have them two dishes separated by 100 astronomical unit, and they send 10 watts across, they can actually measure each other's position, or the distance between each other to centimeters in a minute time scale. Like
Oh, wow.
we're just
Okay.
really good at ranging.
Yeah. All right. Yeah. That's impressive.
You wouldn't ever want to communicate the FRB data. You would, because communication is hard, but like they can range, and so that allows them to then figure out where where the locations of the spacecraft are.
Right. Yeah. Oh, that's really fascinating. And it is, I'm glad you sort of took it right to the nth degree. That essentially over time, the limit of this observatory really just becomes what is the farthest possible radio burst that can be detected by these things. But the problem with radio bursts is that they occur in kind of randomly across the sky. So what would be their kind of field of view? I guess all of them would be staring at the same field of view to try and catch the same radio burst happening.
Yeah, this is a really good, wonderful question. So there about 2% of these fast radio bursts repeat. And so it's actually a lot easier just to take the constellation of spacecraft and point at these repeaters and wait for them to repeat. The distances for these repeaters are like wonderful. Like for this 500 million light years is a pretty typical distance. And even it looks like the distribution is pretty wide in redshift. Like it's like kind of like a logarithmic. Like if I just from eyeballing we don't have a huge amount of data on this yet. It turns out though that I'm not sure it's that interesting to measure the furthest FRB distances, because where the uncertainty in our cosmological model is greatest, unless there's some really weird evolution for dark energy, is the lower redshifts, which is closer distances. Because we think that matter dominates the universe in once you get to 10,000 million light years, or 1,000 million light years. It's of course it's interesting to go to further distances, but it's where the action is at, where we know weird things are going on, is relatively like not the furthest objects.
Yeah. But I don't know, like it feels to me like I've done other interviews with people about ideas like this, that large triangles, that you can discover some really interesting things with some large triangles. So are there other applications that you would be able to do with an interferometer this big tuned to look at radio signals?
Yeah, and that was part of this NIAC study. It was just to come up, like, because this would not be, it would be like a huge endeavor. And so of course, measuring the expansion of the universe is super interesting. And so we thought of a couple other science that could be interesting. So one is that the dark matter we expect to be clumpy on very small mass scales. So, for example, weakly interacting massive particles, WIMPs, which is our leading model for what the dark matter is, model in quotes. We expect a lot of it to be in Earth-size clumps. And when I say a clump, the clump is like maybe a parsec or a tenth of a parsec. It's huge. So like very diffuse Earth-sized clumps or Earth mass clumps. If you have this fast radio burst light going through the universe, it's going through a lot of these dark matter clumps. And this is called a Shapiro time delay. We actually, from the solar system, we can detect the mass of planets in the sun by this type of delay.
Right, because the clocks are going to run slower during the time that it spends in these clumps.
Yeah, that's right. That's right.
Right.
So the gravity of the clump is going to affect the propagation.
Right, and that the more of this time dilation that you measure, that means it's probably going through more clumpy as opposed to more diffuse.
Yeah, exactly. And so like
Right,
what
okay.
you kind of expect, so then you have this sea looking through the universe, and there's a sea of these little dark matter clumps, and they're moving because most things in the universe are moving several hundred kilometers per second. And so they're moving hundreds of AU on your time scales. And so what you expect is that the FRB, if you like monitor a repeating FRB, it will jiggle from these time delays at about the level that these instruments are sensitive. Maybe that's not exactly true for the weakly interacting massive particle. The signal maybe is a little bit smaller if we're talking about tens of AU, but maybe by the time we're getting to hundreds of AU separations, this is not the case. For the spacecraft, there are a lot of models where the dark matter is clumpier. And in fact, even a really well motivated model, which is maybe our second favorite model for the dark matter particles, is an axion that's motivated by quantum chromodynamics. And in these axion models, you can actually get a lot of small scale clumps that are clumpier than the WIMP models. And then we're predicting that this signal is potentially detectable. And so this would be really interesting. So it would probe dark matter models. And then you can imagine a lot of other dark matter models, primordial black holes, and that this is constraining. So constraining the clumpiness of the dark matter on Earth mass scales, which is way, way, way smaller than we were able to constrain the clumpiness of dark matter with other methods. Like in cosmology, we're often talking about like 10 to the 7, 10 to the 6 solar mass. This is way, way, way smaller. And then one other science that we thought of was that you could have these dishes point towards each other and send just a sine wave, and gravitational waves, as they are traversing the array, will distort the space-time. And for the low frequencies that this would be sensitive to, so we've detected gravitational waves potentially. There's a signal that looks to be real for these pulsar timing arrays, and of course we have LIGO, and in the future we're gonna have LISA, which is gonna probe like hundredths of hertz. But it turns out that we don't have really good technology at millionths of hertz. And so this would be potentially sensitive at millionths of hertz. And at millionths of hertz, also kind of like the nanohertz that the pulsar timing arrays are probing, the strains are much larger. So the distortions are much larger. And so you don't need as much sophisticated instrumentation as for example, LISA, and especially LIGO. And so
what would be generating that kind of frequency?
Oh yeah, it's, merging supermassive black holes is something that is definitely there. And then there are other ideas. Like another thing that would generate that is, I think at AU scales, if there's a black hole falling into Sagittarius A star, the black hole in the center of our galaxy. And then there are other ideas.
What about like primordial, like going back to the ones caused by the Big Bang? Like
yeah, that's right. I think it's actually in an interesting range for probing interesting temperatures, interesting times in the Big Bang. So yeah, that as well. Yeah.
Yeah. Oh, that's really interesting. We haven't described it. What are you calling this?
We're calling it the cosmic positioning system.
Right. That's cool. So the next step up from the global positioning system.
Yeah, that's right.
Yeah. And so you have sort of done your deliverable to NASA. You've sent off your phase 1 NIAC grant.
Yeah.
What's next? Wait for phase 2? Hope for phase 2?
Yeah, I definitely phase 2 is on the horizon. What I'm currently trying to do is mobilize the fast radio burst community to get better observations of these repeating fast radio bursts, because I think maybe the aspect of this that is the most uncertain is that the for most of these radio telescopes are detecting fast radio bursts at a gigahertz or 1.5 gigahertz, and it's really best to do this at 3 to 6 gigahertz. And we have a bunch of detections at 3 to 6 gigahertz. We just don't like to find FRBs at 3 to 6 gigahertz because the field of view of our radio instruments is a lot smaller than at lower frequencies, longer wavelengths. And so we mostly just, when some of these repeating FRBs just go crazy at some time, and like then we point all of our radio telescopes at them and we observe them at higher frequencies. And I think we need to do that a little bit more, because like some of these details, like whether I need a 6-meter dish or an 8-meter dish or a 10-meter dish, because you really want to detect of order 100 of these at least with CPS. And so this is something that I think we'll learn in the next 10 years, and then maybe sooner if we work hard at it, even much sooner. Then I think it makes more sense to then do a design study to see like what if I put all of these atomic clock, dish, and the other components that I need, what does this look like? And and then we would probably use like a JPL engineering team to do a study.
Yeah. Matt, question I always ask my guests: what are you obsessed with right now?
Yeah, I mean, I love FRBs, and so I definitely am obsessed with this electron frac thing that we were discussing in the beginning, because this chime array is actually going to release their 5,000 detected FRBs imminently. In fact, initially they had planned to release it in July, and so once these come out, I have like so many science things that I think we can do. That and so I'm hoping that this comes out, and then this weak lensing science, baryon science, I think even like some important steps can be made.
Well, it all sounds absolutely fascinating, and thank you for both the big explainer on FRBs and then how we can use them to measure the expansion of the universe. Matt, thank you for your time, and good luck with being awarded a phase 2.
Oh yeah, my pleasure. Thank you so much for interviewing me.
I hope you enjoyed that interview with Dr. McQuinn. I'm going to give you some final thoughts, but first, I'd like to thank our patrons. Thanks to Abe Kingston, Andrea Pedretti, Barely Griffing, Brian Bodie, Caradwin, Chuck Hawkins, Commander Balick, Cooper Nelly, Dark Finga, David Giltonen, David Matz, Evan Pro, Greg Feely, James Clark, Janice Smith, Jeremy Mattern, Jim Burke, Jordan Young, Josh Schultz, Marcel Smits, Michael Purcell, Nordspace, OneStepForAnimals.org, Ren Kaidi, Richard Williams, Sean Sargent, Stephen Foundlemunley, Team 49, Telescopes Canada, Wolfgang Klotz, and Zeldaborg Galactic Defender, who support us at the Master of the Universe level. And all our patrons, all your support means the universe to us. Well, this is great. This is like 3 ideas all mashed together, and it's the best, right? We've got a NIAC award, and the sort of not what's the idea for the NIAC award, but how did it go after you completed 2 years of research into the idea thanks to the NIAC grant. We've got the Hubble constant. We've got a way to try to be able to measure the expansion rate of the universe. And then we've got interferometry, where we are building this gigantic constellation of satellites that are going to be observing the same targets together and give us these really fundamental answers about the nature of the cosmos, and not just measuring the Hubble constant, but measuring colliding supermassive black holes and other interesting phenomena. So this is like my perfect interview. It's really combined everything all together. And I look forward to the argument in the comments where people discuss why light travels at different speeds moving through different media. All right, we'll see you next time.